Welcome back. In this class, we're going to talk about covalent bonding. Now, there's a few differences between this type of bonding and ionic bonding, but it's basically the main difference is how the electrons are arranged when you form the bond. When something forms an ionic bond, you have the complete transfer of electrons from one atom to another atom. But with covalent bonding, you actually have the sharing of a pair of electrons between two atoms. Now, when this happens, you will form a molecule. Now, the word molecule, there's two words that people come across and confuse them. We have molecule and we have compound. Now, they might be the same thing or they might not. It depends. A molecule is where you have two or more atoms that are bonded together, specifically covalently bonded, but anyway. So an example of a molecule would be water. Water has three atoms that are bonded together, therefore it's a molecule. But another one is oxygen. An oxygen molecule has the formula O2, that's two oxygen atoms bonded together. Another one would be nitrogen. Two nitrogen atoms bonded together. Now, how a compound is different to a molecule. Compounds are made up of molecules, but they are not necessarily the same thing. A compound is two or more elements that are chemically combined or joined together. An example of a compound would be water. Water is made up of hydrogen and it's made up of oxygen, so two different elements that are bonded together. Another one would be ammonia, which is NH3. It's made up of nitrogen and hydrogen chemically combined. If we look at the formula for elemental oxygen, which is O2, this is a molecule, but it is not a compound. It can't be a compound because oxygen is made up of just oxygen atoms. It doesn't have a second element. So just be careful with your language. All compounds are made up of molecules, but not all molecules are compounds. It depends on what the formula is. So just to kind of reiterate that, I'm going to get rid of this and we're going to do a little bit of a pop quiz, we'll put it that way. Okay. So for my first one, if I was to give you NH3, ammonia. Ammonia is a molecule. Your atoms are covalently bonded together, but it also has two elements that are chemically combined. So therefore it is a compound. The next one, if we were to look at hydrogen, this is a molecule of hydrogen. There's two hydrogen atoms, but it is not a compound because it only has one element in the formula. If we look at methane, methane is a molecule and it is also a compound because it's made up of carbon and hydrogen. Ozone, O3, that is a molecule of ozone, but it is not a compound because there is only one element in the formula. Now, that's the difference between a molecule and a compound, and that language, we're going to be using that quite a bit over the next few minutes. First of all, we need to talk about what forms a covalent bond. Now, when we did ionic bonding, I said ionic bonds form between generally a metal and a non-metal. Covalent is different. Covalent bonds will form generally between two non-metals. So two substances on the right-hand side of your periodic table. Now I'm going to flash up the periodic table here. If I walk over to it, now remember, when you are deciding what part of the periodic table are metals and what are non-metals, you start underneath boron and you draw your little staircase the whole way down. The metals are on the left-hand side and the non-metals are on the right-hand side. Hydrogen is also a non-metal. So if two elements from the right-hand side of the periodic table and hydrogen form a bond, most of the time, 9 times out of 10, it's going to be a covalent bond. Now, in a little bit further down the line, we're actually going to look at electronegativity and using electronegativity values to predict bonding. So for now, I just want you to recognize that if two things are on the right side of the periodic table, they're going to form a covalent bond. We'll talk about exceptions later. Right, so two nonmetals. Now, when you have two nonmetals sharing a pair of electrons, why do they do that? They will do that to obtain a stable outer octet. Now, that's the language that we need to be using in the exam. Another way or another phrase that you can use instead of that would be to satisfy the octet rule. Okay, so this is where you're going to have a full outer energy level, or with 8 electrons in the outer energy level, or the outer shell. Okay, now that phrase there, when this comes up in bonding, is going to get you 3 marks. So that's one that you're going to have to learn off. Now, similar to ionic bonding, why do things donate and gain electrons? It's to get a stable outer octet. Covalent bonding is the same. It's just they don't have the same pull on the electrons because the fight between the two atoms is more equal. So it's not like one element can rip electrons off the other one like we have in ionic bonding. Now here, this will all link back to electronegativity and that pull for the electrons in a little bit. Now, in our notes, there's a little bit of theory that goes with this. Now, by forming the covalent bonds, your atom becomes more stable. Your atoms will not exist on their own in nature if they don't have a stable outer octet. They want to be more stable. Next, the noble gases, so the group 18 or the group 0 elements, they are not going to form bonds. Nobody mentions xenon. They don't form bonds. That is because they already have a stable outer octet. If it's in group 8 or 18, they already have 8 electrons in their outer energy level. So they don't need any more electrons. It will also be why, if you look up the electronegativity table for the group 18 elements, they don't have electronegativity values because they don't form bonds. Don't mention xenon. Next, it's difficult now. There's a phrase here in my notes that I actually want you to highlight. It is difficult to establish an atomic radius for the group 0 elements. Now, that specific wording in that question came up in 2021, where they had to explain why, and it got them 3 marks, but it was a really nice question. Now, we've already seen similar questions to this already. Now, what this was getting at, it's not actually getting at Heisenberg's uncertainty principle, like we saw previously. Here, I'm just going to draw out argon. So argon in the periodic table has an atomic number of 18. I'm not putting up the mass number because it's not important. Now remember, your atomic number is the number of protons in the nucleus. In a neutral atom, protons equals electrons. So I have 18 electrons to fill in. Here's my nucleus. N is equal to 1. We'll have 2 electrons. N is equal to 2. We'll have 8. N is equal to 3. We'll have 8. So your group 18 elements already have a stable outer octet. But when we go on and we look at the trends topic, one of the definitions that we'll come across is the definition for atomic radius. What this specific question is asking you is, why is it difficult to figure out how wide this atom is? And it actually comes from the definition for what an atomic radius is. Now, what we're starting to see here is, we're going to take a leap, and you're going to go with me for this, but when we cover atomic radius a little bit later, then when you come back and have a look at this, you'll understand fully what it means. It's just, there's a lot of things in chemistry that they're interlinked, and in order to get one of them, there has to be something else that will feed into it as well. By the end, it will all make sense. So here, normally, if I wanted to figure out what the atomic radius of an element is, so say for example, that's an atom of hydrogen. Now, when you're measuring the atomic radius, you don't measure the radius of one atom. What you actually measure This is a hydrogen molecule. What you actually measure is the distance between the centers of the two atoms, which is the nuclei. So if the nucleus of this hydrogen is here, and the nucleus of this hydrogen is here, when you measure the atomic radius, you get the distance between two nuclei of atoms of the same element, and then you get half of it, because that is going to give you half that distance from the nucleus to approximately the edge of the atom. Now, the problem here is with argon is not going to form any bonds. So you can't get the distance between two nuclei of argon atoms because you don't form an argon molecule. Argon exists as single atoms on its own. It will not form bonds. So my answer here would be argon is monoatomic. That means one atom on its own. And argon does not form bonds to argon. Now, it's not enough here. A lot of students got caught out where they said argon does not form bonds. No, it doesn't, but in order for you to measure the atomic radius, it has to be specific and link it back to the definition that you're saying that it doesn't form bonds to another argon atom, because that's how you measure the atomic radius. To argon. Now, either one of those answers would have got you 3 marks in 2021 when it came up, but it is something that is a bit of a nitpicky, nasty question in my opinion. So now when you see it in your exam questions, you know what you're going after. Now, okay, there's something I'm going to mention here because we will see it when we get to VSEPR. And it's this idea that we have bond pairs and lone pairs of electrons. Now, all of the electrons in an atom are not equivalent. They don't all do the same thing. They have different jobs. It depends on whether they're involved in bonding or not. Now, in some cases, so if I was to draw an atom or a molecule of water, the formula of water is H2O. 1 oxygen and 2 hydrogen atoms. If I draw in the oxygen here, now in a few minutes I'll show you how to draw structures properly, but just go with it for now. Oxygen is in group 6, so it has 6 electrons in the outer energy level. And we form 1 bond to each hydrogen. Now, there's 2 different groups of electrons on that oxygen atom. You have these electrons here, which are not involved in bonding. They are called the lone pairs. And oxygen, in this case, has 2 lone pairs. Now, they are grouped together as a pair. We don't say that there's 4 of them because there isn't. There's 2 pairs, and in total there will be 4 electrons, but we call them 2 pairs, or 2 lone pairs. Now here, in this bond between the oxygen and the hydrogen, you have 1 electron from the oxygen and 1 electron from the hydrogen. This is a pair of electrons, but it's involved in bonding. We call that a bond pair. And again, it's 1 bond pair here, but then you have a second one here. So oxygen, if I was asking you about the structure of it. So oxygen, according to this information, has 2 lone pairs, and it also has 2 bond pairs. Now, I'm setting you up for success here because in a couple of classes, we're going to be going through something called VSEPR, and you absolutely have to be able to pick out the number of lone pairs and bond pairs on the central atom, because that's what VSEPR is. It's using the lone pairs and the bond pairs to explain why the shape of a molecule is what it is. And it's usually worth 6 marks in the exam. Right, that's all I'm going to mention on that for now, but it is a precursor to something we're going to see in a little bit. Right, let's talk about how to draw our dot and cross diagrams. Okay. Now, in our notes, we have a page that's going through how to do this step by step. But the key idea here is we're going to try to get to 8 electrons in the outer energy level. The exception will be something that only has one energy level, because then you put a maximum of 2 in there. Now, the rules for dot and cross diagrams here are the same as when we did ionic bonding. N is equal to 1 can hold a maximum of 2 electrons. N is equal to 2 can hold a maximum of 8 electrons, and 3, etc. Now, when we draw dot and cross diagrams, I know we've already seen in atomic structure that the Bohr diagrams are not the best representation of what's going on with electrons in an atom. However, for the purposes of Leaving Cert, we're going to use the Bohr diagrams to explain covalent bonding. And there is a little bit of a shortcut when you're drawing these diagrams. You don't have to show all of your electrons. You just care about the outer ones. Okay? Now, before we dig into this, when you're asked to draw a structure in the exam, I need you to watch out for a particular phrase. If the exam question mentions anything to do with shape, then you have to draw the correct shape in your answer. So if the exam question was, draw the structure of a molecule of water taking shape into account, then it would have to have a V shape. If it doesn't mention shape, your examiner is not going to be nitpicking on shape. So if it just asks you to draw a dot and cross diagram for ammonia, and it just leaves it at that, then all I want is ammonia. It doesn't matter how you arrange your atoms as long as there's a correct number of them and the electrons are correct. Right, so underneath. Worked example, draw a dot and cross diagram showing the covalent bonding in water. So I'm drawing water, which is H2O. Right, in order to do this, you have to figure out what element or what atom is going to be in the center of the molecule. When you have the formula like this, we know water is H2O, it's why I didn't write it in. Now, water, you look for the element where there is only one atom in the formula. In this case, there is one atom of oxygen. So that is what we are going to call the central atom. And that's the one that you draw first, because everything comes off of that atom. Now, before I do anything else, this question did not mention shape, so you can draw it linear, you can draw it upside down, you can do whatever you want. But I'm going to draw the correct shape. Now, central atom is oxygen, so we're going to start with the oxygen. Now here, this is where your periodic table is incredibly useful, so I'm going to flash that for a second. We need to find oxygen in our periodic table. Now, oxygen is over here on the right-hand side. It's there. And it's in group number 6. That means oxygen has 6 electrons in its outer energy level. Okay, and I'm going to write that in. So oxygen is in group 6, therefore it has 6 electrons in the outer energy level. Now, for oxygen to become stable, it wants 8 electrons in its outer energy level, therefore it needs 2 more. If you were to draw the structure of oxygen, is it going to be easier for oxygen to lose 6 electrons to get a full outer energy level, or gain 2? It's easier to gain 2, or to share 2. Now, with that, oxygen generally will form covalent bonds. It depends on whether it's attached to a metal or not. But in this case, your hydrogen is attached to your oxygen. Therefore, you have a covalent bond between the two. Now, you have 6 electrons in the outer energy level of the oxygen, and it needs 2 more. Where does it get them? It gets them from 2 hydrogen atoms, one of them, 1 electron each. Now, for hydrogen, I'm going to draw this one over here. This is in group 1 of the periodic table. Therefore, it has 1 electron in the outer energy level. Now, before we all go nuts and go, but how can that get 8? When it only has 1 electron, that electron is in n is equal to 1. And n is equal to 1 can fit a maximum of 2. So hydrogen only needs 1 more electron to be stable. Now, drawing it, you draw your central atom first. So that's my oxygen. Right, when you're drawing the dot and cross diagram here, you can draw it in 3 different ways, and they all mean exactly the same thing. I draw this in a very specific way because when it gets to VSEPR, the method that I use here is going to make VSEPR a lot easier for you. Now, if you draw them as the Venn diagram structures with the circles, that's absolutely fine, but it just might make your life more difficult down the road when we get to VSEPR. It's not wrong, so keep going with it if you like it. Now, we said there's 6 electrons on this oxygen. So I'm going to draw them in. Now, it needs 2 more electrons. So if I draw in a hydrogen, that hydrogen has 1 electron. Now, to form a bond between the oxygen and the hydrogen, oxygen is going to share 1 electron with the hydrogen, and hydrogen will share 1 electron with the oxygen. And by sharing that electron with each other like that, that means the hydrogen now has a stable outer, we'll call it a stable outer octet, but it's not 8. It does actually have a full outer energy level because it has 1 of its own electrons, and oxygen is sharing 1 with the hydrogen. That gives the hydrogen 2 electrons in the outer energy level. Oxygen has 6 of its own and 1 from that hydrogen. That's not enough. It needs another 1. That's why when we write the formula for water, there has to be 2 hydrogens. Because unless there are 2 hydrogens attached to the oxygen cannot have a stable outer octet. Now, if you're counting your electrons, you say the oxygen has 6 of its own, 1 from this hydrogen to give you 7, and 1 from this hydrogen to give you 8. Now, I've shown the correct V-shaped structure, but in a question like this, unless it mentions shape, don't worry about it. Another way that you can draw this, and it's perfectly acceptable, a lot of people don't like this to show the sharing of electrons between the hydrogen and the oxygen, and that's fine. So instead, you could draw it like this, where you show the electrons like that, indicating that they're being shared. But as you can see, it's quite difficult to show that dot and cross diagram if you were then to take shape into account. You would have to, that's how it would have to be drawn, and it's a little bit awkward. Another one is with the overlapping circles or the Venn diagram type circles. So I'm actually going to draw that one here. So you have your oxygen in the middle. Draw the outer energy level. If you want, you can draw the inner energy level electrons, but they're not involved in bonding, so it doesn't matter. I'm after getting pen all over myself. Great. So there's the 6 electrons in the outer energy level of oxygen. You form a bond between the oxygen and the hydrogen. Your orbitals have to overlap to form that bond. And now, in the overlapped space between them, you have your 2 electrons. Hydrogen has 1 of its own and 1 from the oxygen. Oxygen has 6 of its own and 1 from that hydrogen to give me 7. And then you have a second one over here, like that. Yeah. Again, it's a little bit awkward to show shape, but you can show shape using that one as well. All 3 of those diagrams are equivalent, and all 3 of them will get you 3 marks. So don't be drawing more than 1 diagram. You just need 1 of them. Okay? Now, on the next page of our notes, rather than going into double and triple bonds, we're going to do a couple of practice questions drawing covalent diagrams involving single bonds first. When you are sharing 1 pair of electrons between 2 atoms, so that's what I have here. You have 1 bond or 1 pair of electrons formed between this oxygen and this hydrogen. That's called a single bond. Now we're going to do a couple of them, the most common ones that appear on the exam. Okay, so the practice questions. Draw the dot and cross diagram for each of the following molecules. A is ammonia. Ammonia is NH3. Now, before you do anything else, you have to figure out what the central atom is here, the element that you're going to draw in first. Now, we look at the formula, and you pick out the element where there is only one of them in that formula. And that would be the nitrogen. There's one atom of nitrogen and 3 of the hydrogen. Therefore, the nitrogen is the central atom. Okay. Now we find nitrogen in our periodic table. It's in group 5. Now I don't expect you to remember that. I just remember because I've taught this for donkey's years. So nitrogen is in group 5. Therefore, it will have 5 electrons in the outer energy level. The nitrogen will need 3 more electrons to get a stable outer octet, and it gets those from the hydrogens. Now, hydrogen, these are what we call the peripheral atoms. Don't worry about that word. Hydrogen is in group 1, therefore has 1 electron in the outer energy level. Now we're ready to go. Once you've figured out that information, you're ready to start drawing in your dot and cross diagrams. Now remember, it's a dot and cross diagram. Dots on one, crosses on the other. Don't represent your electrons using the same symbol. The examiner has relaxed that a little bit, but on some mark schemes, they are a bit nitpicky. So we're just going to cover ourselves here. Now we draw in the nitrogen first because that is my central atom. We have to fill in the 5 electrons in the outer energy level. Now, when you're doing this, with practice, you will know when something has lone pairs. So as I've drawn that in, there's 5 electrons on that nitrogen. Now, from experience, I know that nitrogen is going to form 3 bonds. So 3 of those electrons will be involved in bonds, and I will have a lone pair. And I know to draw that. In a second, I will draw a diagram of a dot and cross diagram where someone would not get full marks. So at the minute, as long as you're showing there's 5 electrons in the outer energy level, we're going to go with that. Now, that nitrogen will form a bond with 1 hydrogen. So nitrogen shares 1 electron with this hydrogen, and hydrogen shares 1 electron with this nitrogen. Hydrogen will have a full outer energy level, but nitrogen doesn't. It has 5 of its own and 1 from the hydrogen to give me 6. That's not a stable outer octet. We need another hydrogen. Hydrogen only has 1 electron, so you can't form a second bond to this hydrogen. So we need a second hydrogen. Nitrogen will share a different electron with a second hydrogen atom, and hydrogen will share 1 electron with the nitrogen. Hydrogen has a stable outer energy level. The nitrogen has 5, 6, 7 electrons. We're nearly there, but it's not stable yet. We need 1 more. So we form a third bond to hydrogen. Now again, none of these questions mention shape, so if you did this with right angles between your hydrogens, it's fine. Now, when you get to here, say for example, you spread out your electrons up there. You had 1 here and 1 here because you wanted them to be spaced evenly on the atom. If I was looking at this from a student, I actually would not give this any marks. Yes, the number of bond pairs is correct, but they haven't correctly shown the lone pair. When you have electrons up here that are not involved in bonding, you should group them together. So I'm going to rub these 2 out, and then you group them together like that. So always check your diagram at the end, and if you have any electrons not involved in bonding, rub them out and push them together to show that they are a pair. That's my ammonia for 3 marks. Now the next one is methane. Now methane is a very common one in the exam. I'm going to draw it down here on the bottom. Methane is a greenhouse gas, so you'll see it in the option topic, but you'll also see it in organic chemistry as well. Now, methane for CH4. Your central atom is the one where you only have 1 of them. That is carbon. Find carbon in the periodic table. It's in group 4. Therefore, it has 4 electrons in the outer energy level, and it needs 4 more to gain a stable outer octet or achieve a stable outer octet? Hydrogen is in group 1, therefore has 1 electron in the outer energy level. Hydrogen only needs 1 more for a stable outer energy level. Now, when we draw these in, you draw your carbon first. Carbon has 4 of its own electrons. Now, it doesn't matter which one you put as X's and which ones you put as dots. It doesn't matter. So if you did them the other way around with the carbon as the dots, it's fine. Nobody cares. Now, draw in 1 hydrogen. Hydrogen has an electron of its own. Hydrogen shares 1 electron with the carbon, and carbon shares 1 electron with the hydrogen like that. Carbon will now have 4 of its own, plus 1 is 5 from this hydrogen. That's not a stable outer octet. We need another hydrogen. So we form a second bond. Carbon shares 1 electron with this hydrogen, and this hydrogen shares 1 electron with the carbon. That means the carbon in the middle now has 6 electrons. It's not stable yet. So we keep going until the carbon has 8 electrons in its outer energy level. And to do that with hydrogen, you need 4 hydrogen atoms in order to achieve that. Hydrogen can only form 1 bond. It can't form more than 1. Now again, I've shown a tetrahedral shape here, but if you did it with right angles between them, that's absolutely fine. It didn't mention shape, and that would be your 3 marks. Now, just in case, because some of you definitely will have drawn the Venn diagram for this one, you have carbon, then you have 4 hydrogens, 1, 2, 3, 4, then you have your electrons in the overlap space between them. Like that. Both of those diagrams are perfectly fine. So don't be stressing about which one is the more correct way to draw. It doesn't matter. As long as your examiner can see the correct number of electrons and the correct number of atoms, you are absolutely in the clear. The only bit that's a little bit dangerous is if you have a lone pair and you haven't grouped them together. The examiner will nitpick on that. Now let's talk about double bonds. So in your notes, this is on page 117. Double bonds are where you are sharing more than 1 pair of electrons. I'm just going to grab the eraser from over here. Single bonds, you share 1 pair between 2 atoms. Double bonds, imaginatively, share 2 pairs of electrons between 2 atoms. Now, there is a very common exam question that asks you about this one. It is carbon dioxide. So, or oxygen. Now, worked example number 1. This looks at a double bond. And I'm going to write under here, we share 2 pairs of electrons between 2 atoms. 2 of the same atoms. Not of the same element though. Now, and a specific example of this is a molecule of oxygen, which is O2. Now, this is not a compound, remember, it's a molecule. Now, oxygen has 6 electrons in its outer energy level. Oxygen is in group 6. Now, in order for it to get a stable outer octet, it needs 2 more. So we draw in 1 atom of oxygen. And then you draw in your second atom of oxygen. Like that. Both of them have 6. When oxygen forms 1 bond with the other oxygen, this oxygen has 6 of its own and 1 from the other oxygen to give me 7. Then it will form a second bond because neither of those 2 oxygen atoms have a stable outer octet yet. So the second bond is the oxygen forms or shares a second electron with that same oxygen atom. So that is what we call a double bond. Now, again, this is perfectly fine to draw it as your Venn diagram type structure. Like this, where I'm grouping my lone pairs together. It's a tiny bit small in there. And now in that overlapped space where you are overlapping the orbitals together to form the bond, you have 4 electrons inside that shared space. A single bond will share 2 electrons, so 1 from each atom. A double bond, you actually have formed 2 separate bonds. Every bond that you form in chemistry has 2 electrons in it. So if you formed a double bond, that's twice the number of bonds, so there has to be 4 electrons shared in total between the 2 atoms. They're not both sharing 4, but there's 4 overlapped between them. Now, if you go to the practice questions, there is a specific example going through this, and it's carbon dioxide. Now, this one I need you to put a star beside because it's a very common exam question. The central atom here is going to be carbon because there's only one atom of carbon in the formula. Carbon is in group 4 of the periodic table. Therefore, it will have 4 electrons in the outer energy level. So I'm going to draw that one in first. Next, oxygen. This is not the central atom because I've got 2 of them, but oxygen is in group 6. Therefore, we'll have 6 electrons in the outer energy level. Okay, so I'm going to draw 1 oxygen in here. Oxygen, I have to fill in 6 of them. Okay. Now, start from this oxygen over here on the right-hand side. It has 6 of its own. It needs 2 more for a stable outer octet. Oxygen will share 1 electron with carbon, and carbon shares 1 electron with the oxygen. Now, that's not enough. The oxygen now has 7 electrons in its outer energy level. It needs 1 more for a stable outer octet. So it forms a second bond to the carbon. It forms a double bond. This oxygen now on the right-hand side has 6 of its own, 7, 8. This oxygen has a stable outer octet, so we leave it alone. The carbon in the middle doesn't. Carbon has 4 of its own, 5, 6. So 6 electrons in total. That's not a stable outer octet. It needs another 2, and it gets that from a second oxygen atom, which we draw over here on the right-hand side, or the left-hand side. How did I pass my driving test when I can't tell the left from the right? So carbon, we have the electron. Oxygen shares 1 electron with carbon. This oxygen now has 7. It needs another one. So it forms a second bond to the carbon. The carbon in the middle has 4 of its own, 5, 6, 7, 8. The carbon has a stable outer octet. Now double check your oxygen. 6 of its own, 7, 8. All 3 of those atoms have stable outer octets. You're done. Now, if you were getting confused with this one and you were like, well, if I draw in the carbon and I draw in an oxygen, how do I know that my oxygen, how do I know the carbon has to be in the middle? Well, from the formula and what we teach you at Leaving Cert level, everything has to have a stable outer octet. If you were to do this, where you put another oxygen over here, and now you don't put the carbon in the middle, we're going to have a problem. Now, hopefully you can see what my problem is. If I formed a double bond between those 2 oxygen atoms, that's great. This oxygen will have a stable outer octet. This one doesn't, because it will also form a double bond to that carbon. The carbon now in the middle has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's not going to happen. So this, you're saying, has 10 electrons in the outer energy level? No, it won't. But the carbon is also problematic because the carbon only has 6 electrons, 4 of its own, 5, 6. So use the rule that I've shown you where when you're looking at the formula, you pick out the element where there's only one of it in the formula. That's going to be your central atom. And it will work for 99% of everything. The one that won't work for is where you have something where it's like N2, H2, that kind of thing. Then you know there is no central atom. Now, let's have a look at a triple bond. There's one triple bond that can come up on the leaving cert in terms of a dot and cross diagram. And it is to draw a molecule of nitrogen. Now, this one I need you to put a star beside. Nitrogen is one of the most commonly asked questions in bonding. Now, it could be to count the number of electrons. It could be to count the number of sigma and pi bonds. It could be to explain the shape or to explain the reactivity of nitrogen. There's a whole variety of different questions that can come up here. So we're going to start nitrogen by being able to draw the dot and cross diagram because that feeds into the other questions that you will be asked. Now, this is going to form a triple bond. Now, nitrogen is in group 5 of the periodic table. That means it has 5 electrons in the outer energy level. It needs 3 more electrons for a stable outer octet. Now we put in our second nitrogen atom. If we form one bond between those 2 nitrogen atoms, neither of them have a stable outer octet. They both now have 6 electrons. So we keep going. We form a second bond between the 2 nitrogens. Now they both have 7. We're not there yet. So they will form a third. Now, that's what the triple bond is. You are sharing 3 pairs of electrons between the same 2 atoms. They don't have to be of the same element, but for this case they are. Now here, if I wanted to count up how many lone pairs and how many bond pairs, you have 1 lone pair on each nitrogen, and technically it counts as 3 bond pairs, but I will amend that sentence a little bit later in VSE Pure. Now, with this, all you need to be able to do is draw the dot and cross diagram. And it has to be clear from your diagram that you're sharing 3 pairs of electrons. Now, if you did it slightly differently, where you don't like drawing the line between them, oops, that's a little bit too small, where you don't like drawing the line between them, that's absolutely fine. A lot of students don't. And you draw it like this. Absolutely fine. It is the same thing. And same if you want to do your overlapping Venn diagram circles, absolutely fine. You'll still get 3 marks at the end of the day. Now, there's a few practice questions coming up. There's 3 pages of practice questions that I strongly recommend that you have a go with. However, we're now going to talk about some of the trickier questions. Now, these are given on page 120 of your notes. And is something that when you see it come up, you need to be incredibly careful because the examiner is setting a trap and the vast majority of students will fall face first in it. Okay. The element that I need you to be careful of is boron. Boron has the symbol B, capital B. Now, if I go to my periodic table, when we did our staircase separating the metals from the non-metals, boron is here. It's in group 3 and has an atomic number of 5. Because the staircase started underneath boron, boron is classed as a non-metal. Now, the most common compound of boron is something called BH3. And this is on page 120 of your notes. So BH3. There we go. It's actually called borane is the name of the compound, but you don't need to know that. Now here, you have boron, a non-metal, bonding to hydrogen, which is also a non-metal. According to what we're doing, 2 non-metals, when they combine, will form a covalent compound. Even though in some of the electronegativity differences, we will see that it should be ionic, it's not. Boron is going to form covalent bonds and it does not form ionic bonds. So here, our central atom is boron and it's bonding to hydrogen. Boron has 3 electrons in the outer energy level because it's in group 3. Now, hydrogen has 1 electron because it's in group 1. Hydrogen will share 1 electron with boron, and boron will share 1 electron with the hydrogen. Great. We keep going until all of the electrons are involved in sharing on the boron. Now, if anyone has eagle eyes, you're going to notice a problem here. Boron can only form 3 bonds. It can't form more than 3. So if you were to count up the total number of electrons that boron now has, it has 3 of its own, 4, 5, 6. That's not 8. It's fine. Boron is an exception to the octet rule. It can't form more than 3 bonds because it only has 3 electrons in the outer energy level. It doesn't have any more electrons available to form a 4th bond. So it can have a maximum of 3 bonds, and all of its electrons in the outer energy level are involved in bonding. Now, even though it's not 8, it's fine. It's stable. Now, again, so there's 2 traps that we can fall into here. Boron always forms covalent bonds, and 2, it actually will not have 8 electrons in the outer energy